Assalamu alaikum, everyone. So what we are going to do, so it's going to be lecture 10 for microelectronics EE341. So we are going to cover multiple topics today. Rather, it's going to be a review of the topic which we have started last time, and then we will conclude another topic about the common mode rejection ratio. And if the time permits, we can do a couple of problems and some related discussion. Again, before the start of the lecture, if you have any query, you have questions, make sure to come in office hours or update. We can have schedule special time. So what we are feeling that the students are not coming in an online class setting. So I don't know, whatever the reason it is. So what we are doing at this moment, we will upload the recorded lectures. You go through those lectures, come in an office hours, update any queries, and we will try to upload the lectures even earlier than the class slot. So you have time, you can go through the content. So just coming back to the topic, last time we discussed was basically the differential pair with an active load. So I will briefly, like for 5 minutes, just give an overview, and then so that we can link that to the story too, and also what we want to conclude. So differential pair with an active load. So we discussed that, okay, why we need first differential pair with active load, what is meant by active load. So if I want, for example, some configuration where I have an amplifier, for example, like this one, it's a current source here. So we have another current mirror. So we have, this is going to be in a load. So it's giving set this VB, which is being set based on this current. Here we have VDD here, we have VDD at this point. And here we have some differential pair, symmetric again. We said V in negative, and we said V in positive. And this is an NMOS, this is an NMOS for sticky. And that's what we said, okay, this is a terminal which is connected to some ISS. So that's what we did. And we said, okay, why we were doing this topology, we are using this topology if we want to drive some circuit, either it's going to be amplifier or a load which is single-ended, but we want a different input to be differential. So our configuration is this: we have a differential input, but this we want this to load this to drive a single-ended load, single-ended. And we mentioned, okay, if we use the normal differential topology, which was a fully differential, what's going to happen? We will lose the half gain. So we don't want that thing. That's why if we do this diode connected, what the benefit we are going to get is that ultimately the gain was not reduced, and that we have seen analytically and quantitatively in the last lecture. And also the analogy active load was coming from the notion that since based on V in going up, V in going down, so as V in plus will go up, the current will go also up, I plus delta I. So delta I will increment, and because of this delta I increment, this VB point will enhance, and this VB point will change the value of this current. On the opposite scenario, the value of current can be reduced or can have a different variation. So at the runtime, this M3 will have a different value of a current, and correspondingly that current will be mirrored through M4 in this branch. So we have actively value of current which is being changed. So that's why we normally call it an active load. So this is a diff pair. If you just want to see, this is a diff pair, and we have an active load which is varying dynamically. That's why the name active load comes. And we derive at the end relation that, okay, if we want to find a relation between V out by V in plus minus V in negative, we concluded that the relation was coming out to be something minus GMN times the equivalent to ROP in parallel with RON. So we were ending up the same relation, which was for the fully differential, or we can, to be exact, we can write, okay, this is almost equal to, okay. So that was the main benefit of using a diff pair with an active load. We can derive, or we can drive a single-ended output, which can be an amplifier, which can be an ADC, which can be a resistive load, anything. So we are not much concerned about that thing. So moving forward, what we're going to cover in today's lecture is basically something which is also related to the differential circuit, and that's one of the main topic which we are interested, the differential circuits again, and that is basically is related to that. The beauty of the differential circuit which we discussed, or which we mentioned, was that it somehow cancel out the common mode value. The common mode value. So the diff circuits, if I want to write diff circuits, basically rejects the common mode value. And what was the common mode value? A noise signal or a DC value. Let's say a noise or a DC for us, DC value, since it's applied to both inputs, it cancels out this thing. So that is one of the main benefits of the differential circuit. But we need to see how much it is rejecting, because it's not only it's going to reject, that should be relative to something which we are knowing. So that's why we need to find out, is it rejecting completely, whatever the value is coming? But definitely we are living in a realistic environment. It will reject it by some numbers. Can be 100 dB, can be 200 dB, can be 50 dB, something like 10 times, 100 times, whatever. But there should be something. So that terminology which we normally called as common mode rejection. So we'll talk about this thing and we'll see why it comes and how it impacts common mode rejection. And then also another thing which is related to it is basically common mode rejection ratio. When we call the common mode rejection ratio, basically it is if I just say the common mode rejection is ACM, a common mode gain of my system. And if I want to talk about common mode rejection ratio, that is basically my diff gain in a fully differential divided by my common mode gain. So if I have something like that, then I will say this is going to be my common mode rejection, which is commonly known as CMRR. If you see any data sheet of amplifier, it will not be complete without the information of a CMRR, common mode rejection ratio. That is pretty much common specifications. It's in the range of 100 dB, 120 dB, 90 dB. So 100 dB meaning that the differential gain is 100 dB times more than your common mode gain. Okay, and ultimately what this means that your signal to noise ratio, because differential signal is something which is our signal desired sig path, and the common mode is a noise for us. Okay, a DC value which we don't want to process through our amplifier, so that is a noise. So ultimately this is telling SNR, signal to noise ratio. We know that more the better the signal to noise ratio, the better the system is. Okay, so system is better. The lower the SNR, our system is not good as you want. I should rather draw not like arrow sign, rather I should make a. So if I do like this thing, my system is better. In this way, my system is not good. Same thing related directly to CMRR. This means CMRR is higher. Okay, so that's something which you need to make sure आप लोग इसको identify रखें, remember रखें. Now what we are going to do, we are going to see a little bit analytically. हम लोग हमेशा करते हैं कि in a circuit from where the CMRR is basically coming. ठीक है, so let's do a little bit. I will just go to the next page because we might not have much content to cover, so we can easily take the next page. So if I draw again a diff pair with some resistive load instead of an active load or a diode or a diode or a MOS load. So I'm just going to put a resistive load. So let's put this M1 transistor, which is an NMOS. Okay. M2. Right. So here we have a gain. Since they are symmetric, so this P is going to be an active AC ground. So here we have some current, tail current ISS. So what we are talking about, we are talking about RD. These two are VDD. Okay. So that's what we are having. Okay. So that's what we can do that thing. Okay. So M1 and M2, if we are missing anything, and now in this case, there is no differential input being applied on M1 and M2. Now we are only analyzing when the effect of a DC value, which is applied to both M1 and M2, meaning a DC signal, which is being here, for example, a DC signal, let's say V common mode connected to ground going to this point, and the same signal, make sure to be attentive on this point. The same signal is not like a short, it's same signal that we do is going to M1 and M2. So if there is an increase here, there's an increase in this point. It's not diff anymore. It's just a common mode signal. So that's why it's common. A common mode signal is being applied on both sides in a similar fashion. Okay, that's one of the most important thing which we need to be careful. Now on top of it, if this is the circuit, everything goes fine. We don't have much issue. Lekin, there is a one bigger issue which comes in the realistic systems. We call them realistic systems because they are not ideal. So they are not ideal. We don't live in ideal world. You design this value to have an impedance of, let's say, 1 mega ohm. Okay, well and good. But there is some variation which occurs. You put that, you do the fabrication, and ultimately it concludes out to be this value is not 1 mega ohm, this is 1.1 mega ohm. Similarly, you design this RD to be 1 mega ohm, but when you do the fabrication, it comes out to be 0.95 mega ohm. You must say, okay, there's a very much small variation. Yes, there is a very much small variation. That's why we need to see the impact of this very much small variation on our circuit. And on top of it, these tail current here, we can have some resistance can also be, which we normally ignore. So can be some resistance which can be also present. So we need to also take into account what's going to be happen with that resistance. So I'm just bringing these things back. But before rubbing that thing, one more important thing which we need to see, why this variation happens, variation in the resistance. That's pretty much common. Again, if you see data sheet of any resistance capacitance, even for the discrete components, even through SMDs or through holes, whichever you see, there is some level of tolerance written. What is meant by that thing? So if you see any resistor data sheet which you use in the lab or you have previously used in your labs, so you will find like, okay, 1 kilo ohm with a tolerance level of plus minus 10%. 1 mega ohm, for example, with a tolerance level of plus minus 5. For a capacitance, similarly, 1 picofarad with a tolerance level of plus minus 10%. This tolerance level is telling you that, okay, we designed it for that 1 kilo ohm, but during the fabrication process or realistic value can vary. Okay, and that's the same variation which I wrote here. This variation is more for the discrete component as compared to the IC design, but still that variation is there. And we need to be careful in our design, and that comes as that common mode gain or common mode value will have a huge impact. If these are exactly equal, we will not be impacted that much. But since they are not equal, we need to be careful. किस तरह careful करेंगे? We need to have some basic analysis. कि क्या analysis हम करें to ensure it's not hurting us, because we need to see ना कि हमारा एक डिजाइन है वो मुझे तंग भी करेगा या नहीं करेगा. Might be this like whatever we design, it's not going to hurt. So I'm just saying that's why this is an RD. ये एक RD है, and this is RD plus delta RD. Small variation है, वो small variation थोड़ी हो सकती है. At this moment, let's not give a number, but let's see the impact of that small RD. कि उसका small RD का हमारे पास overall impact क्या होगा. So first of all, there is asymmetry. We know that. So now we need to see whether the current is going to be the same or no. That's the main important question for us. So as we know, the current is going to be governed by this M1 and M2. Okay. So since it's going to be in saturation, so there will be ID1 here and ID2 here. In the normal differential pair, we normally say that, okay, the same voltage, if it's being applied here, width and length are same voltage applied, ID1, I1 will be ideally should be equal to ID2. So if we want to write the relation of ID1, so ignoring again the channel length modulation, we can write half mu1 Cux, okay, W1 by L1, right, times VGS1 minus V threshold n whole square. I'm ignoring the channel length modulation. So or we can say lambda is equal to 0. Again, assuming lambda is equal to 0. If I want to find the relation of ID2, that will be also equal to half mu n Cux. Same thing, exactly similar, omega 2 L2. Though we will keep the M1 and M2 as we last time also mentioned that M1 and M2 should be identical devices. And then we have VGS2 minus V threshold. And we can see that we are applying the same potential at this point. So since the potential is same, we must have VGS1 equal to VGS2. So VGS1 will be equal to VGS2. Omega 1 by L1 is equal to omega 2 by L2. Since they are identical devices, the rest are constants. So we can easily say whatever that delta RD is coming, that is not affecting me, at least in the form of a current. So I can write ID1 will be equal to ID2, even if there is some variation in the this value is coming in terms of delta RD. So this delta RD is not affecting us at this moment if we just talk about the current. But what about other variation which is going to come because of some other impact? Let's analyze them. Okay, so now let's move on and let's analyze a little bit. Next page. So if we want to draw again, let me draw the same circuit just for easiness so we can see the behavior easily. So we concluded that the value of RD variation is not affecting us in terms of a current at least, but that's not all. Delta RD. So the current here is the same, VCM. Same VCM is going to this node, right? And this is the interesting point. These are those 2 points which we normally call Vout1, for example, and Vout2. Okay, these are the 2 output points. So we are interested in basically the final output will be what? Vout, for example, 2 minus Vout1, right? So that will be the final output. And because of that variation, जो इसमें थोड़ी सी variation होगी VCM में on both sides, there will be some change in the current. In normal scenarios, अगर ये delta RD ना होता, the Vout CM अगर मैं लिखना चाहूँ will be equal to 0. Why? Because the same ID variation, ID delta ID times delta RD minus delta ID times delta RD will be equal to 0. But this is not true in this scenario. Why? क्योंकि हमारे पास जो RD है, there is a delta RD with that. So now new Vout common mode is equal to delta ID, जो variation है because of VCM की variation की वजह से, That's RD plus delta RD minus delta ID RD. So जो हम लोग इसको भी बेनिफिट कह रहे थे कि because of this delta RD variation current is remaining same, so हमें नुकसान नहीं हुआ, rather we are having some disadvantage. Because of this thing, an output common mode value is coming which is not a desired value. अब उसको किस तरह हम लोगों ने खत्म करना है, we need to look into it how we can get rid of it. So value है क्या, delta ID times delta RD. वो जो स्मॉल जितनी वेरिएशन करंट की टाइम्स रेजिस्टेंस की वेरिएशन के साथ वी आर गोइंग टू सी दैट फिनोमेना. सो अब हमने उसको देखना है कि हाउ मच इज बीइंग अफेक्टेड. डेल्टा आरडी डेफिनेटली हमें गिवन होगा, जो भी वेरिएशन होंगी या वी कैन एज्यूम, बट वी नीड टू फाइंड आउट व्हाट इज दिस अमाउंट ऑफ डेल्टा आईडी. उसका रिलेशन किस तरह हम लोग निकाल सकते हैं, दैट लेट्स फिगर इट आउट हाउ वी कैन फाइंड डेल्टा आईडी. सो since this ID current जो हमारे पास वेरिएशन की वजह से मूव कर रहा था, that is moving through this point, ठीक है. So यहाँ से करंट कितना था, delta ID from this side was coming, this point. Let me use a different color. So delta ID was coming from here and delta ID was also coming from this point. So जो RSS से होगा इस point पे, आप potential is going to flow because of this 2 delta ID current. दोनों current add हो जाएंगे. और वो potential कहाँ add होगा? If I just want to replicate my VCM will not be now only this VGS. अगर मैं उसको खाली कह दूं कि delta VCM में variation कितनी होगी, will not be equal to delta VGS, बल्कि वो variation will be based on this RSS value. तो वो हो जाएगी 2ID RSS. Right? So now moving forward, if we have this expression and if we want to replicate something, हम लोग कह सकते हैं, we know all of us know कि आपके पास GM क्या होता है, GM is equal to delta VGS. आपके पास जो GM होता है that is delta ID by delta means small variation times delta VGS. We all know that thing. So we can replace this one. Delta VCM is equal to delta VGS will become delta ID by GM plus 2 times delta ID times RSS. Okay, and we can easily take out ID common. So ID will be equal to 2 ID 1 over GM plus 2 times RSS, which will be equal to delta VCM. Now our interest was what? We want to find this value of small delta ID, जो उस VCM की variation की वजह से आई है. तो वो delta ID क्या हो जाएगा? We can directly take to the left hand side. Delta ID will be equal to delta VCM divided by whatever this relation, 1 over GM. Let me just write if I can along. Okay, I will write it here. I'm writing this expression here. So delta ID will be equal to delta VCM times or divided by 1 over GM plus 2 RSS. And that is something which we need to be careful. Okay, now we can bring it back and put in this expression. इसमें place in कर देते हैं and we can see how much delta V out will come. So if we want to bring up or delta V out, which was equal to essentially, so and again might be the sign can be negative because it was a diff pair, so we can write even minus delta ID times delta R out. If we want to do V out minus V1 minus V2. So as we are comfortable, you can do that thing. So we can replace this delta ID from the previously calculated delta VCM value. So VCM divided by 1 over GM plus 2 RSS, okay, times delta R out. Right? So we can just do some simple manipulation that how much is this relation. So we are concerned with this thing. हम लोग क्या देख रहे हैं? We are seeing the variation at the output by small common mode variation in the input, which I normally called ACM, common mode gain. ठीक है, जिससे हम diff gain find करते हैं, so ultimately we find the common mode gain here. So ACM की value क्या आ रही है? We are having minus, it's again an inverting configuration, we can see minus delta R out. Just a 1 minute. Did I use a different terminology here? Yeah, we are using RD. We just start using R out, it's RD. So we were using, this is RD in our all analysis previously. Let me replace back. Yeah, sorry for this thing. So it's delta RD we were using. Just again, the naming convention, nothing more than that. So it's going to be 1 over GM plus 2 RSS. Okay, so it's again a common mode gain. And if also we can write, okay, if RSS, since they are adding together, if bigger than 1 over GM, so we can write it, approximate relation can be minus delta RD divided by 2 RSS. Okay, that's also a common mode gain approximate expression. Okay, so that's one thing. We can also do the similar using another expression, but in a just couple of moments. But at this moment, I would like all of you to make sure all of you absorb this thing. It's a simple, but this is known as common mode value or common mode gain. Now, how this is related to the common mode rejection ratio? CMRR will be equal to AD differential gain divided by ACM. Differential gain kya hoga? We need to figure it out. And then we can divide it by common mode gain and we can find the expression. So let's try to find the differential gain. So we get an idea कि हमारे पास system में differential gain कितना है. So the same जो हमारे पास circuit था, let's draw it again. So exactly same. Then we have here some ISS. Now at this point, यहाँ हमारे पास this is a V in negative. This is a V in positive, meaning this is going to be increased, this is going to be decreased. It's a differential analysis. Now we are not doing common mode anymore here. We are doing a differential analysis, and this is RD and this is RD. So we are not seeing the delta RD variation now. So we are just analyzing कि अब क्या होगा. This is V out plus and this is V out minus. Okay. So we are interested in finding V out plus minus V out negative divided by V in plus minus V in negative, and that would be equal to AD, the differential gain. So now we know that this is, अगर ये आपके पास एक differential pair है, so it's going to be symmetric. This is going to be AC ground. Why AC ground? Same amount अगर यहाँ increase होती है, same amount V in decrease, V in negative decrease होगी. Ultimately, no current will flow through this point. So it's a virtual ground and an AC ground. So we can use it as a ground, and that helps us. We can sort out our circuit in a similar manner. RD, VDD. This is the virtual ground, and this is your V out. So that's something. Agar lambda is not 0, so V out by V in. Now we know that that is equal to minus GM times RD in parallel with R0. ठीक है, ये आपके पास diff हो जाएगा. And in the previous configuration, we have figured it out that जो हमारे पास ACM था या CMRR था, that's equal to AD by ACM. AD क्या था? Minus GM RD in parallel with R0. And if we just want to write the expression which we just found in a previous one, or ultimately the variation थी that was equal to RD में जो variation, this is also some variation in that one, RD में variation थी divided by in the form of whatever the relation we figured it out was. Let me just double check. In the previous one we found out, yeah, so we mentioned 2RD divided by RSS. So RSS was the source one for us, so we can represent with that source one. Right, so here the RSS is going to come as it is, तो हम इसको RSS के तौर पे जो इसका impedance आ जाएगी, so we can have 2 RSS. So that's what we are going to have in this expression, and then we can find the CMRR overall. If there is some variation, it's going to be cancelled out. They will be cancelled out. So ultimately, R naught is going to be infinity. So RD is going to be cancelled out. So we will be left with minus GM, or minus will be cancelled. So it's going to be GM divided times RD by 2 RSS. RSS will come up. So it will be 2 times GM times RSS, which is ultimately the resistance or the value of impedance seen at this point. So if you want an RSS, or you can also write this equivalent to the impedance, or a very much high impedance, which we can represent with the half of RO. So that will be equivalent to RO. So CMRR ultimately will be a bigger value if we follow this topology. But again, it totally depends upon which one topology you are using. But one important thing also to do the common mode configuration for the common mode gain. We can also do common mode gain using the same differential approach which we have seen. So how we can do that thing? We just mentioned this stuff that okay, we have here something RD, right here RD. We just, if we want to see another way, which we all are familiar using a small signal model, and here we have some ISS. Okay. So again, now we are talking about same value VCM being applied here, and same value of VCM is being applied at this node. Okay. So अब हमारे पास क्या होगा कि the same current is being flowing here, same current is being flowing here. So if I want to represent this or replace this current source में क्या होगा? Current supply current, there will be some resistance जो हम लोगों ने भी RSS के साथ किया था. So that's going to be RD. That's going to be RD. Yeah. So here again, I'm just writing separate VCM. So otherwise the line unnecessarily goes from here. So we have here VCM. So if we do this one, and here this is ground, this is ground. So here अब मैं क्या कर रहा हूँ? I'm just representing this is with some the current source with some impedance. उसको हमने RSS कह दिया, जिस तरह हम लोगों ने कहा था. Now when we are doing this thing, what we are ultimately analyzing here, that there is some variation which is ultimately happening. वो variation क्या है? For V out. Same current is flowing here, same current is flowing here. पहले हम लोगों ने क्या किया था? We treated this point as a virtual ground, right? We treated this point as a virtual ground, but in reality, we cannot treat this as a virtual ground in a common mode configuration. Why? Because इस RSS में से कितना करंट फ्लो करे? अगर यहाँ से ID1 है और यहाँ से ID2 है, the current flow will be ID1 plus ID2, and on top of it, ID1 is equal to ID2. So this means यहाँ से 2ID current flow कर रहा होगा. Okay, so that's very much important. From a resistor, कोई resistor है RSS, उसमें से current flow कर रहा है 2ID. ठीक है. आप अगर सर्किट को सेपरेट करना चाहें, and if you have some configuration like this RSS हो और आप कहें उसमें से ID current flow कर रहा है, but ultimately the potential जो VSS है that should remain the same. So क्या करेंगे? यहाँ VSS के लिए क्या था? VSS was equal to, how much was it? 2ID times RSS. Okay. So now what we should do with this impedance, that ultimately the overall potential at this VSS remains same. क्योंकि अब एक branch में से current जो move करे, that is ID, so that we can again separate the circuits. So this means the impedance has to be twice. अगर twice impedance होगी, the VSS will be again 2ID times RSS. So मैं इस ऊपर वाले circuit को भी separate कर सकता हूँ in two separate circuits, VDD, RD, and V out. Okay. So, and I replace here VCM, grounded here instead of RSS, or instead of virtual ground जो हम लोग differential में लेते थे, we can put a 2 RSS here. Okay. And the opposite will be also the same. So दूसरे के लिए भी same होगा, average out. So again, half circuit will be enough to analyze again the common mode gain. एक तरीका हम लोगों ने पहले देखा था, but we can also do in this fashion. Let's a little bit do further analysis किसका gain किस तरह निकल सकता है. So हम लोगों ने जो conclude किया, we concluded this. This is my VCM. And यहाँ से what it is? It's 2 RSS. And what is this point? It is RD, which is a VDD here. And this is my V out. मैंने क्या find करना है? Common mode gain, which is equal to V out by VSM, जो हम लोगों ने शुरू में find किया था. किस तरह find करेंगे? If you just see, it's again what we already have saw. So हमारे पास वही जो amplifier है single stage की, वही या current mirror ही कहीं fit होके आता है. The same thing is being applied here. We have a common source with degeneration. हमारे पास एक common source with degeneration configuration है, so we can easily find now our gain. तो क्या उसमें gain होता है इस केस में? So we will have a GM, अगर direct लिखना चाहें, GMRD divided by 1 plus GM to RSS. ठीक है? And then we can say, okay, this 1 plus GM to RSS will be equivalent to GM to RSS because that's bigger value. So we will be approximately related to, approximately we will be GM RD divided by 2 GM RSS. GM will be cancelled out. So we will be end up with again negative sign will come. It's an inverting configuration. So we will be left with RD divided by 2 RSS. ये वही relation है जो हम लोगों ने, if you remember, start में ये find किया था. Let me just see. 1 second. Yep. Yeah, we found rather next page. So here is the same relation जो हम लोगों ने यहाँ find किया था. Common mode gain minus delta RD or minus RD by 2 RSS. So we reach to the same thing. Either we use the small signal model, which we are all familiar, or we figure it out in a different configuration. हम लोगों ने find क्या करना था? We just want to find something which is a common mode gain. अगर same voltage आप input पे apply करें, what's the behavior on an output side? ठीक है? So यहाँ तक we have covered almost all of the things related to the differential or a diff pair. One or two important things I will just update you for your information. It's not going to be that you will be examined on these things, but definitely they are very much helpful, and then we can conclude our lecture. So similar to this configuration, there is another terminology which we use, like we called a CMRR, which we just say a common mode rejection ratio. Okay, so it's very much important. But apart from this one, for any amplifier, specifically for the differential amplifier, another value is also written, which is called at a PSRR plus, PSRR negative. Think over it. What is the PSRR stands for? Last thing we can write, okay, it's a rejection ratio. It's a rejection ratio. So, but the PS stands for power supply. And plus meaning positive. And power supply negative rejection ratio. अब ये क्या होते हैं? So, जिस तरह हम लोगों ने इनपुट साइड पे कोई कॉमन मोड सिग्नल आता है, उसका आउटपुट पे बिहेवियर ऑब्जर्व किया एंड उसको डिफरेंशियल सिग्नल से कंपेयर किया कि हाउ मच और डिफरेंशियल सिग्नल इज स्ट्रॉन्गर एज कंपेयर टू कॉमन मोड. सिमिलरली आपके पास ये जो ट्रांजिस्टर था, सिंपली बना लेते हैं RL. ठीक है. So you have this transistor RL, उसको कोई सप्लाई प्रोवाइड हो रही है VDD. सप्लाई इज अगेन अ कॉमन मोड सिग्नल. आप इनपुट पे नहीं दे रहे बट इट्स अ कॉमन मोड सिग्नल. उसमें या डीसी सिग्नल है, उसमें कोई वेरिएशन हो, व्हाट्स इम्पैक्ट ऑन दीज 2 पॉइंट्स, राइट? सो इसका इम्पैक्ट भी अगर हम आउटपुट पे देखना चाहें तो दैट इज समथिंग व्हिच वी गवर्न इन द पावर सप्लाई पॉजिटिव रिजेक्शन. अगर मैं ग्राउंड का, ये मेरे पास फॉर एग्जांपल ग्राउंड टर्मिनल है, उस ग्राउंड टर्मिनल में कोई वेरिएशन होती है, उसका इम्पैक्ट इफ आई वांट टू सी ऑन द आउटपुट साइड, so then that is known as a power supply negative rejection ratio. किस तरह? So PSRR positive is a power supply rejection ratio. तो क्या होगा? अगेन पहले टॉप पे डिफरेंशियल सिग्नल, क्योंकि हम लोग जो कंपेयर कर रहे हैं विद आवर डिफरेंशियल सिग्नल जो हमारा मेन सिग्नल पाथ है. तो डिफरेंशियल सिग्नल डिवाइडेड बाय गेन ऑफ पावर सप्लाई पॉजिटिव या AVDD. डिफरेंट टर्मिनोलॉजीज आर यूज्ड. AVDD. ठीक है. PSRR नेगेटिव क्या होगा? अगेन डिफरेंशियल सिग्नल डिवाइडेड बाय A. नॉर्मली हम ग्राउंड को VSS भी कहते हैं तो AVSS लिख देते हैं. बट अगेन all of these variations are used. Again, this is very much important thing you should know कि PSRR क्या होता है, PSRR negative क्या होता है. You can again find कि किस तरह आप find कर सकते हैं. AD is already known to you. AVDD plus you can figure it out कि how you can find the AVD. If you, for your interest, you want to try, you can just try, and if you have some confusion, please feel to send an email or ask in the office or in the next session. But again, just do these things because that's really helpful and really interesting. And if you see any data sheet again, you will find this power supply rejection ratio. So you can again deal these things. These are value will be written in 100 dB or something, which is telling you okay how much good. Again, bigger value, good thing. Why? क्योंकि हम लोग signal divided by ये value ले रहे हैं. So bigger value means your signal is good. So आपका जो सिस्टम है वो सिग्नल को ज्यादा अच्छा पास करेगा, नॉइज को रिजेक्ट करेगा. That's why it's known as rejection ratio. So that's all for basically today. We are making a smaller lecture so that we want to complete the diff pair, and I would highly recommend make sure to go through lecture 9, which you have done things in the previously regarding the active load, some calculation. Those small signal analysis is very much helpful. It's a revision, but make sure make your hand dirty. Unless you don't make your hand dirty, you will not be able to solve, or you will not be able to make yourself equipped with these techniques, because there are something fundamental and something you need to acquire the skills. That needs practice too. And analog design or analog IC design need recursion. Recursion means you have to revisit your designs, revisit your techniques again and again. Otherwise, it's like something you will start getting away and it will take more time. So make sure you spend some time. It's a worthy skill. It's going to help you, and it's something which makes you link to the things around you. So all hardware is basically everything is using these things. So it will make you again link to those things, and free feel to ask anything. And if you have any confusion, we can have a separate session for those things. Thank you, and make sure to listen to the lectures. Thank you very much.